Jai Hind. Today our topic of discussion is Tower of Hanoi. This is one application of stack. So in this particular lecture, we'll start with what is a stack, what type of data structure it is, what are the operations that can be performed with the stacks, and then we will discuss the application of stack, Tower of Hanoi, how a stack can be used to solve the game problem of Tower of Hanoi. So starting with the stack. So firstly we are going to cover up what is stack, what type of data structure it is. So first point is, it is a linear list. It means we are storing the data linearly. There is a linear relationship between the elements. What type of elements we are going to store? That is same type of elements. A stack is a linear list of same type of elements in which an element may be inserted or deleted only at one end, and this one end is called top of the stack. So it is a data structure in which we store the same type of elements, same data type element, and the insertion and deletion both occurs at the one end, and that one end is called top of the stack. When we implement stack, the record of this top is kept with a subscript value or the top pointer. So simply we say that there is one top pointer that keeps record of the stack. Any insertion or deletion that is done at the top of the stack. So as we say, as we said that we are doing insertion at the top and deletion also from the top. So actually we are having something, this type of logical structure. What this logical structure is, we are having this type of storage, means we are storing something, then putting something on the top, then on top of that, and so on. So what is done? The insertion is also insertion is done at the top as well as deletion is done from the top. If we talk about the real life examples, we can talk of this idli stand. In this, what we do, we put idlis on one dish, then we put another on the on this one, then another on the top, and so on. So this is stack. If we take different discs of varying size, so one is put at the bottom, then one above this, another above this, and so on, and when we will pull it up, we will pick it up, we will pick from the top. So this is a stack. So as we are taking out the element or the dish which we put at the last, so that's why we call it last in first out or first in last out. So actually the stack is a LIFO type of list in which whatever is inserted at last will be deleted at first. That is last in first out. So that is our stack data structure. When we have stack data structure, we use special terminology with this. The insertion in stack is called push and the deletion is called pop. So push is the term used to insert an element into the stack, and pop is the term used to retrieve an element from the stack. And when stack is empty, we say it is underflow if we try to delete something, and overflow is the condition when we want to insert something but already it is full, so there is no more space to store anything. When we are having the empty stack, it means the stack contains no element. So the top of the stack is present at the bottom of the stack. And when we say stack overflow, it means the stack is full. So the stack top is present at the highest location of the stack. We cannot move it further up. So that is the condition of overflow. So we'll use these terms: push, pop, stack empty, stack overflow when we talk about some stack. So let us understand the concept with help of few numbers. Let me say I am having a stack, this is my stack. If I have to insert a value 10, so where is top initially? It is empty stack, so top is at the bottom. So let me say I am inserting 10. So what will happen? Top will be incremented. So it will point to the first location. Initially it was at the bottom. Now it will point to the first location and 10 will be inserted there. Now if we have to insert 20, so again what will be done? Top will be incremented. After incrementing top will point to the next location after 10 and we will insert 20 here. And now if we talk about deletion, so what is at top? We will retrieve the element from top. The top element is retrieved, so 20 we have deleted, we have displayed it and we have retrieved wherever we want to use it, and top will be decremented. So after decrementing top will point to this location, that is next to 20. So what was inserted at last, that was 20, and whatever is deleted at first, that is 20. So last in, first out. This is one stack. So this is the way stack works. We will now consider one application of stack, that is Tower of Hanoi. Tower of Hanoi is a game problem. In this problem, we are having 3 pegs A, B and C. We are having 3 pegs A, B and C, and peg A, there are placed a finite number of disks, let me call that n number of disks. And how these are arranged? These are arranged in decreasing size. It means the biggest is at last level, then smaller than that, and so on. So it is in decreasing order. Now we have to do what? We have to move all the disks from peg A to peg C. So what we were having? We were having 3 pegs A, B and C. Let me call it A, B and C. Okay, few disks are available here. Let me say just 2. These we have to shift to C in the same order. In the same order means these must be placed such that the larger is at bottom and the smaller is at the top. And what we have to do? We have to shift from A to C and we can take help of peg B. This is our B peg. Okay. So now how this is solved? This can be solved with help of recursion, and in recursion what we use, that is stack. So it is actually one application of stack. With help of recursion we can do this, we can find the solution of Tower of Hanoi. Okay. Now we have to shift these to this with one more condition, that at one time we have to move only one disk from one peg to another. For example, I cannot, when I am having these two, I cannot pick both and put here. No, I have to move one disk at a time. So the conditions are written here. Only one disk may be moved at a time. Specifically, only the top disk on any peg may be moved to any other peg, like our stack. At the top, whatever is present, that you can move to some other and you can put only on the top. So that is the stack implementation. At no time can a larger disk be on a smaller disk. That is what we have discussed, that it should be in decreasing order from bottom to top. So this is our problem. Now how can we solve it? This we have taken one example with 3 disks. I am having here peg A, B and C. If I consider here, I am having green as the biggest disk, then white comparatively smaller and red the smallest. So what we have to do? We have to shift all these in the same order to C. So I want actually this type of condition, this is my goal. Now how to do it? When I have to maintain this order, and one more condition, that I cannot move more than one disk at a time. Okay, so this is one possible solution. What is the solution? The red is put here. We can take help of B. So from A, one red disk is moved on C. Now the white, in the second step, white is moved to B. Then next step, red is moved from C to B. In next step, from A to C, green is moved. So we got this condition. Then red is moved from B to A. After that, white is moved from B to C. After that, red is moved from A to C. So we got the solution. Okay. When we got this solution, there are some steps. In this step, one disk is moved from one peg to another peg. Now, how to find this sequence? How to decide this sequence? We are able to find the solution, but how to decide this? So, for this we can use stacks, we can use the recursive algorithm to solve the problem of tower of HANOI. So, now let us discuss the steps. So, what is the general solution? Rather than finding a separate solution for each n, we use the technique of a recursion to develop a general solution. What is that general solution? We are having three pegs, A, B and C. From A, I have to move all the disks to C and I can take help of B. Okay. So, what are the three steps of general solution? Move the n-1 disk from peg beginning to auxiliary. It means from A to B. What is beginning? A. What is end? B. What is C? That is auxiliary that we can use. So, we can list out here. I am having A peg, B and C. From A, I have to move to C. So, this is my beginning, this is the end peg and this is auxiliary that I can use. I can use this auxiliary peg to move data. Okay. So, what the point is, move the n-1 disk from peg beginning to auxiliary. Okay. So, as the largest one is to be moved to C, so all the disks above that will be shifted to B. All the disks. It means just leave the last one. So, it means n-1. So, n-1 disk from beginning to auxiliary we will shift. Then how many will left on A? Just one. So, that will be shifted to the end. n-1 has been shifted to auxiliary. Okay. And this one left will be shifted to C. Now, what the point is? We cannot shift these n-1 at one go. So, that is why we are saying that we are using the recursive method. So, we are when we are shifting n disk, then n-1 will be shifted to the other one which is not currently in use. Currently in use means which is not current destination. So, the current destination was C. So, what we did, the n-1 pegs have been shifted, the n-1 disks have been shifted to B, the auxiliary. Now, what we did, after shifting n-1 to auxiliary, we shifted the last one to the destination, the end. Now, whatever has been shifted to auxiliary will also be sent to end. So, that is our third step. Move the top n-1 disk from auxiliary to end peg. These are the three steps. In this, how many moves will be there? 2 to the power n-1, where n is the number of disks. Okay. So, now let us understand how these steps move. How do we take these steps to determine the order of the sequence of the steps of moving one disk at one time from one peg to another peg. So, let us understand this with help of two disks. So, what we are considering? We are considering that we are having two disks. Okay. So, we are going to solve the tower of HANOI. So, my problem is tower of HANOI. How many disks are there? 2. Where these are placed? On A. I can take help of B to shift these disks from A to C. So what I said, the tower of Hanoi problem is there. I am having A peg, B and C peg. A is my beginning, B is auxiliary and C is the end peg. I have to shift two disks which are arranged in decreasing order on A. Now I need to shift these to C. So what are the three steps we talked about? We said that when we are having n disk, shift n-1 top disk to auxiliary. Okay, so what we will have, we have to do the recursive problem, recursive solution of what? I have to shift n-1. n-1 means 2 minus 1, that is 1. What I will do? I will shift from A, not to end, to auxiliary. What is my auxiliary? B. I will shift it to B, and if I need, I will take help of the auxiliary, that is C. Okay. C will be auxiliary in this case. This was auxiliary when I was shifting from A to C. Now I am shifting that to B, auxiliary, and for this, if I need some help, I can take help of C. Okay, now what happened? Only one disk is left at A, so I can directly shift that. The second step. One top I shifted to B. Okay, B is auxiliary in this case. I shifted to B. Now one is left on this, so I shifted that to end. End is C in this case. Okay. Now what we did? We shifted one disk temporarily to B. So this disk which is present currently on B will also be shifted to C. So tower of Hanoi, the recursive call, will go on doing recursive calls until we get the final move. The final move will be represented like this. A to C means move one left disk on A to C. Okay. Now what we did before doing this, one disk we have shifted to B. Okay. So the disk 1 which is placed on B will be shifted to C, and if need, take help of A. So one disk was shifted from A to B, that has also been shifted from B to C. So finally A to B, B to C. So finally that disk is also getting shifted to C. So now because we are having just one disk, so we will shift it from A to B, and again one disk, so we will simply shift from B to C. So if we understand it, then I am having these three, A, B, C. Here I am having two disks in decreasing order. So first shifting is from A to B. First shifting is from A to B. It means this particular disk is placed here. Second shifting, take from left to right. Second is A to C. A to C. What is there on A? This larger disk. Shift that to C. It means this disk has been shifted to C. What is next step? Whatever is placed on B top, shift to C. So what is on B? This smaller disk, shift to C. So these three steps are used to shift the two disks from A to C. So that is our recursive call, recursive general solution to find to solve the tower of Hanoi with two disks. Now we will understand this with three more to elaborate more the concept of recursion. So here I have taken 3 disks. So it means I am calling tower of Hanoi for 3 disks, I have to shift from A to C and I can take help of B. So what will be my first step? My first step will be n-1 shift to auxiliary. Okay. So how many disks are there? 3. So how many I have to shift to auxiliary? 2 minus 1. Okay. What is my beginning point? A. What is my auxiliary? B. So I have to shift 2 disks to B. How many will left at here? Just 1. So shift simply that to C. A to C. 2 shift to B, then 1 is left on A, shift that to C. Now the 2 which has been shifted to B will also be shifted to C. So another call. The n-1 disk that have been shifted to B will also be shifted to C via A if required. Okay, now how many are there? 2. So what I will do? Again the general solution 3. 2 minus 1 means 1. n-1 disk I will shift to auxiliary. Tower of HANOI 1. Where I will shift to auxiliary. Okay, so from where? Source, that is beginning. What is auxiliary here? C. What is end? B. Now how many are left here? Just 1. So shift that to end. What is beginning? A. What is end? A to B. Okay. So next is 1 we have shifted from A to C. So shift that also to C to B. 1 which has been shifted to C will also be shifted to B. And if needed, take help of A. Okay. So what happened here? 1 left only. So simply we can move from A to C. Okay. Only 1 left here. So simply we can move from C, it is from C to B. So we have to do 1 shift from A to C, then 1 shift from A to B, then 1 shift from C to B, then 1 shift from A to C. Now we'll take the other recursive call. What was the other recursive call? Tower of HANOI call 2 disk I have to shift from B to C. Okay. So this is n-1 I will shift to auxiliary. So what is my call? 1 I will shift from this beginning to auxiliary. What is auxiliary here? A. If needed, take help of C. Now how many are left here? 1. So simply shift that to beginning to end. What is beginning? B. What is end? C. Now to do this, what we did? We shifted 1 to A. 1 disk we have shifted from B to A. This disk which has been shifted to A will also be shifted to C. So 1 A to C, if needed, take help of auxiliary B. So this is just 1. So what we will do? B to A, beginning to end, just 1 disk. So simply beginning to end, A to C. So our steps are A to C. A to C. A to C means the top disk is shifted to C. Top from where? A. So from A, if I see top is red, so that has been shifted to C. Now what is second step? Disk from A is shifted to B. What is on top of A now? That is white. So white is shifted to B. Now what is next? Top of C is shifted to B. What is on top of C? That is red. It is shifted to B. So red is shifted on white. Okay. Now what is done? Whatever is in top of A, that is shifted to C. What is on top of A? Green, that has been shifted to C. So this situation has become. Now whatever is there on B, top shift to A. What is on B top? Red. So that shifted to A. Next is whatever is on B top, shift that to C. So on B top there was white, so that is shifted to C. Okay, and now what is there? What is on top of A? Shift that to C. What is on top of A? That is red, so that is shifted to C. So we got these 1, 2, 3, 4, 5, 6, 7 moves. It means 2 power 3 minus 1, that is 7 moves we applied to shift 3 discs from beginning peg to end peg, from A to C, and B is taken as auxiliary here. So in this way we can go for any number of disc general solution. Just what we need to do to shift n disc from A to C, will shift n minus 1 disc from A to B, B is the auxiliary. Then we will shift the one left from A to C, and in third call what we will do, whatever we shifted, how many have shifted? N minus 1. The n minus 1 that we have shifted to auxiliary will also be shifted to the big end peg. So these are the 3 solutions, 3 recursive calls to find the solution of tower of Hanoi for any number of disc. So the program, we can input the number of discs, and I am taking here as number of discs, and tower of Hanoi problem is called for A, B and C, 3 pegs. So if n is 1, only 1, then simply move disc from beginning to end. There is only one disc on the peg, so it will simply be shifted, because we can shift the disc on the top, and there is only one, so simply will shift. Otherwise we will have the recursive call. What is the recursive call? The Hanoi recursive call for n minus 1 disc. What we will do? We will shift n minus 1 disc from beginning to auxiliary, taking help of the last end peg, and then there will be only one left at beginning. That one left at beginning will be shifted simply to end, and at last the n minus 1 which has been shifted to auxiliary will also be shifted to end. So this is the general solution for tower of Hanoi problem using stacks. Stack has been used here, it is an application of stack. So in this particular lecture we talked about stacks, different operations that are performed on stack, and then we discussed the tower of Hanoi game problem that can be solved for any number of disc, that is general number of disc n, in which we shift from A to C in the same order, one at a time. So that general solution we have discussed here. Thank you.